Hello class, good day. Welcome for our continuation lecture for our major losses, head losses in pipelines, for our subject hydraulics engineering. So today we will focus more on the difficult problems where we will be conducting iteration examples for us to solve for the friction factor, for the velocity, for the discharge, for the head losses. Okay? So let's begin. So previously we have solved this problem, right? If you can remember, this is basically a type 1 problem where we are to identify the discharge, and given the head loss, and we are to identify the friction factor, and given also the type of pipe, in this case a galvanized pipe. Now let's talk about what about the problems that cannot be solved directly. For example, a problem that can be solved directly is one in which we are trying to determine the flow rate, but the total available head is given instead of head loss. So here are the step-by-step procedure, or part of the. Let me use my laser pointer. Part of the available head is lost to friction, and part of the head remains as kinetic energy in the jet as it leaves the pipe. So in this case, you will have a velocity here. So for us to iterate function of friction and the velocity, uh, we are to write the energy equation to guess an initial value for the friction factor, solve for the velocity, calculate the Reynolds number, update the friction factor, and if new f different from the old f from your step 0, go to step 2. So repeated process. Okay? So it's easier said than done. Okay, so let's look on this example first. So in this case, we have a standard temperature 20 degrees water or fluid that is to be that is to run through to this pipe with length L, equivalent to 200 meters with the height of 4 meters, and the diameter of the pipe is simply 0.005 meters or 5 centimeters. What is the discharge through the galvanized iron pipe? So the galvanized iron pipe, given the type, will give us a Ks of 0.15 millimeters. So your roughness is equivalent to Ks over D. So that will be 0.0015. Again, we are to convert this to meters in order for you to cancel the units. So divided by 0.05, the diameter is simply 0.03. So at a standard temperature of 20 degrees Celsius, it will give you a kinematic viscosity of 1 times 10 to the negative 16, negative 6 rather. So again, the first step is to write the energy equation or the Bernoulli equation. So from point 1 here to point 2, the pressure at point 1 is 0, static 0 velocity with a height from the datum of 4 meters as we can see here. Since you will have a jet at the outer, you will have a 0 plus the datum of 0 plus the velocity unknown, okay, plus the head loss, okay. Since you will have head losses, so the summarize of the head losses concerned with from the opening of the pipe, from the length of the pipe is simply HL, okay. So in this case, F or L over D, V squared over 2G from your raised back equation, okay. There's your raised back equation. So solving for V, we can have this function, okay. We can have this equation. So 2G4 over 1 plus F multiplied by L over D. So the friction factor is still unknown. So the length is 200 divided by 4. Okay. So why is this simplified now? Simplified L over D. So 200 divided by 0.05. That is 400. So 2 times 9.81 times 4, that is 78.5. So sorry about this. I haven't write the whole functions or whole values of the variables. We are to assume an initial value for f. So here's the crucial part. Okay, assume the initial value for f. How will you approach that? Here is a good estimate. Okay, here is a good estimate. A good initial estimate is to pick the friction value that is valid for fully rough pipe with a specified relative roughness. So, the roughness is 0.003. So, that came from here, okay? So, this one. So, assume a friction equivalent to that. So, very straightforward. Approximately 0.026. Right? Now, so from this function, with a Reynolds number or the friction factor equivalent to 0.026, you just simply input the following. Okay, the roughness and uh, the friction factor will give you one equation with one unknown here. Once you input F here. So given that 78.5 over 1 plus 4,000 multiplied by 0.026, getting the square root of it will give you a velocity of 0.865. Now let's look. For us to check, we need to identify the Reynolds number. So the Reynolds number is simply the velocity multiplied by the diameter of the pipe divided by the kinematic viscosity here. So that is 4.3 times 10 to the 4. Now we obtain an updated estimate for F from the Moody diagram. Let's look again. So given the friction factor or given the Reynolds number and the roughness of 0.003, let's look on 4.3, so about here, right? Times 10 to the 4 with a roughness of 0.003. So cross-checking, that will be this line, okay? This red line, or let me highlight it for you to see. So this red line, okay? So this is our uh, the line that we are concerned with in this diagram. So the intersection is this point, okay? So we are now to omit this later, 0.026. We are now concerned with the new iterated value of f of 0.029, okay? So from the cross-check from the Moody diagram, 0.029, inputting it to your equation here, will give you simply a velocity of 0.819. So close from the previous iteration with 0.865. Now for final check, we are to identify again the Reynolds number using this velocity now. Okay? So dV, the same computation, diameter multiplied by the new velocity divided by the kinematic viscosity will give you now a Reynolds number of 4.1 times 10 to the 4. So it's kind of close, okay? From 4.3 to 4.1. So that will give us, actually this, our next iteration was 0.294, okay? So but then the approach is almost the same. Okay, so very close from 0.29 and almost close. There, the solution converges to 4.07, so approximately 4.1, okay, times 10 to the 4. So we can simply assume a velocity of uh, 0.814 from our 0, 1, and 2 iterations, and solving further for us to get the discharge. So that will be 0.814 times 10 times pi times the area, the diameter divided by 4, diameter squared divided by 4 will give us 1.6 times 10 to the negative 3. Okay? So I hope you understand, class. By the way, we'll still have many problems, so hold on to it. Okay? So, next problem. Okay, next problem. In this case, we are given a cast iron pipe. The type of pipe is given. The length of 2 kilometers. Diameter of 0.3 or 300, 300 millimeters. Determine the maximum flow rate with the maximum allowable head loss. Given also the head loss. So this is a type 2. Okay, type 2 problem given the kind and size of pipe and the head loss. So simply use the Darcy-Weisbach equation, FL over D multiplied by V squared over 2G. So solving further, we have one equation with two very special unknowns. So the velocity and the friction factor. So as we said earlier, that the friction factor is a function of the Reynolds number. Okay? So you cannot easily identify this. But let's find first the kinematic viscosity. So from the formula, inputting the temperature which is equivalent to 10 degrees Celsius here. So solving further, we get 1.31 times 10 to the negative 6. Now how about the Reynolds number? So that is 0.3 multiplied by the velocity, which is still unknown, right? This is still unknown. Okay, so we have an equation 2. So later, we only have two equations, but we will use the friction or the Moody diagram for us to iterate the guess values for the friction factor. Solving for the roughness, that will be simply the property of the roughness divided by the diameter of the pipe will give us 0.0009, okay, or 9 times 10 to the negative 4. Now, looking at this equation or the trial one, actually this is a very what you call this, an ugly guess, okay? Because as we said earlier, your initial guess should be close to the function of the roughness, right? From the line of the roughness, in this case, in this line, okay? In between 0.008 and 0.001 is 0.009, right? So at least you should guess already 0.02. But the initial guess here, 0.01, will give you. So solving further, inputting here 0.01 will give you a velocity of 1.16. And inputting this 1.16 here will give you a Reynolds number of 2.668 times 10 to the 5. Take note of that. So that is about here. Okay? So, take a look. You don't have any values in this intersection. Right? In this intersection, in this line, and in this line, 2.6. So, no line. No curvature. We don't have what you call this. We don't have a reason for this deal to assume that friction factor. Okay? But then, uh, let's now look on another iteration. So, again, our relative roughness is 8.67 times 10 to the negative 4 or approximately 9 times 10 to the negative 4. So, trial 2. So, this is the good guess using 0.02. Right? So, this one. So, using that one will give us a Reynolds number of or a velocity of 0.82 and a Reynolds number of 1.886 times 10 to the 5. Now that is very good guess. So in between here, right? So solving further, we will get an equivalent, friction factor here of in between 0.25. So this 9 times 10 to the negative 4, this length, and this y value of 1.886 times 10 to the 5 will give us a friction factor of about 0.21, right? 0.21, or in this case, we assume as 0.02. Or the initial guess is 0.02, but from the Moody diagram, this is what we have, 0.021. So finally, solving further, use that to substitute here. So we will have a value of velocity of 0.82, and inputting 0.82 to equation 2 will give you a Reynolds number of approximately this one again, so closer. And then inputting this to the area or the function or the equation for discharge velocity times area will give you a discharge of 0.058. So that is our answer for your discharge. Another solution, or next example rather, where to compute the discharge of a 3 meter diameter. Again, the diameter, or the 3 meter here is the diameter. The wood stave pipe in its best condition carrying water at 10 degrees Celsius. It is allowed to have a head loss of 2 meter per kilometer of pipe length. So given the head loss and given the discharge, this is a what type of problem? So this is type 2 problem given the kind of pipe and the wood stave. So solving, we can simply have the Darcy-Weisbach equation. So again, you will have one equation with two unknowns, two variables. But then the friction factor is a function of Moody diagram. Take note of that. Now the wood stave with a roughness of 0.18 to 0.9, we take 0.3. Okay, we assume 0.3. So I guess this is a book problem, no? So E 0.3 divided by the diameter of 3. So that will be, this is a you need to correct this class, ha. Sorry about this. This is 3 times 10 to the 3. Okay? So 0.3 divided by 3 times 10 to the 3 kasi you need to have the same units. So the roughness is 0.001. So at 10 degrees Celsius, you have a kinematic viscosity of 1.31 times 10 to the negative 6, which gives us the Reynolds number with function V of 2.29 times 10 to the 6. So this will be your equation 2. This is your equation 1. Okay? So solving for iteration from iteration 1, we will have a function of velocity 2.45 meters per second. Now from the Moody diagram, we will have the Reynolds number, or substituting to equation 2, right? So in this case, 2.99 times 10 to the 6 multiplied by 2.45 will give you a Reynolds number of 5.6. So from Moody diagram, we will have an updated value of 0.10122. So solving further, we will have the following. So approximately close with a Reynolds number of 7.2. Plus, I haven't shown here I think the diagram, because I want you to look on this. So it has converged here already. So our initial guess is already correct. I keep on asking what another solution, because maybe or later on we will look. Final problem. Our final question is the discharge velocity times the area, 22.27 cubic meters per second. Another solution, this one. Okay, you can simply use this formula. Okay, but then still using the Moody diagram. I was supposed to say free body diagram. I'm combining my concepts from other subjects. From Moody diagram, that will be 0.0121. So substituting very straightforward, we simply get the velocity to be 3.15 meters per second, which is approximately equivalent from the previous uh, answer. Okay, so simply inputting the value of f here. Okay, so if you will have any question, class, you may comment down below, message me in Facebook or in my email address. Okay, so that's this one. Okay, so from your terminologies or from your equation a while ago, this value and this line, so the Reynolds number is simply uh, The Reynolds multiplied with the friction factor is 9.62 times 10 to the 5. So this is this one. So in between 8 and 10, the 6 to the 6, right? So 9.6 times 10 to the 5 in this case. And this line, or the roughness of 0.001, will give you an approximate friction factor of 0.0121. So you may also use this equation, okay, or this line, those lines, those, okay. So an easier approach, okay. Now here's the crucial, or here's a much critical part. We're talking about now the problem type 3. So given the kind of pipe, the head loss, and the flow rate, we are to identify the diameter or the size of the pipe. So here are the steps. Use the Darcy-Weiss box, solve for the diameter, calculate for the roughness, calculate for the Reynolds number, update the friction factor, solve for the diameter. If new diameter different from the old D, go to another iteration. So looking at this problem, a pipeline is designed to carry crude oil. So take note, class, that uh, we are not always concerned with water. Though the most common of hydraulic engineers have practiced with dams, with flow, with pipes through water, where water is the main parameter, okay, the main variable of change, right? But in this case, in this problem, we'll talk about crude oil with a different specific gravity and a different kinematic viscosity, with a discharge of 0.10 cubic meters per second and the head loss per kilometer of 0.50 meters, 50 meters per kilometer. What diameter of steel pipe is needed? Available sizes are 20, 22, and 24 centimeters. So two equations, the Darcy-Weiss back and the continuity equation of discharge. So solving further, we just simply solve for the diameter. Okay, arrange the terms. So the diameter will be a function of the friction factor. So that will be D is equal to 0.440 times F to the 1/5. So make an initial guess for F. So this is a safe assumption, right? So before a while ago, we have assumed a broad assumption of 0.01. So in this case, we will use 0.015. We have no idea why the book tells us this assumption, but essentially it will give us a diameter of 0.190 meters or 190 millimeters. Now, you can have an idea here, class, because this diameter is close to the diameter, right? The given options. So it is safe to say to have a friction factor or a guess that will give you a diameter close to these values. So take note of that. Now we can calculate the relative roughness and the Reynolds number. So from the roughness, since the roughness is dependent to D, inputting the 0.190 here, right? So that one to this one will give you a value of roughness of 0.00024. Okay, so solving further, you can also solve the Reynolds number, right? So VD over mu, you have the velocity. You have the velocity given from the assumption of the diameter. So in this case, you already have the discharge. You can simply solve for the velocity given the, what you call this, the velocity and the area, because the area is dependent through the diameter. But since you have the expectation or an assumption for the diameter to be 0.190, you can use that. Okay, so solving further, we will get the Reynolds number to be 66.8 times 10 to the 3. Okay, so using these terms, so again, from the Moody diagram is a function of the roughness and the Reynolds number. we can have an updated value or updated assumption for the friction factor, right? So let's look. By the way, class, the roughness from the steel pipe, it is assumed here that 0.046. So that will be here. So commercial steel, right? So close to 0.04. Actually, the range is 0.045 to 0.09. But the assumption here is 0.046. Okay? But in this cases, class, I can give you the assumption. Pag may mga problems, when I will give problems, I will be the one to give the standard for steel pipe. Okay? So, again, we have the Reynolds value. So, the updated friction factor, which gives us the 0.0024, with a Reynolds number of 66.8 is 1. So, about here, 66.8 times 10 to the 3. 10 to the 3. Tama ba? 66.8, tama. Times 10 to the 3 kasi ito eh. Times 10 to the 3. So, when you move the decimal point here to the back, that will be 6.68, right? Times 10 to the 4. So, sorry about the vandalism here. So, in this, our reason for the D line, so that we will call this RFD line, no? So, the line that we are concerned for the friction factor will give you a friction, for the Moody diagram, will give you a friction factor, the intersection of Ks, or the roughness, to the 6.68 times 10 to the 4 will give you a friction factor of 0.021, which is kind of far from 0.0515, right? But then, let's now use this for the next computation, next iteration. So, using 0.021, so from the Reynolds number or Reynolds function, input F here. So, you can simply get the diameter of 0.203. So, ito na. Nakikita na natin. It's kind of close to 20 centimeter and 22 centimeter, right? So, the Reynolds, once you get the diameter, the Reynolds number is a function of the diameter in this case. So, 0.203, input it here. So, the Reynolds number is 62.5 times 10 to the 3. And going back to your roughness coefficient of 0.00023, using again this now, the Reynolds number and the new roughness. Use this to have an updated function of F, right? From the Moody diagram. So, that will be again this one. 0.0024, Reynolds number of 62.5, about here. So, still close to 0.021, right? So, the solve or the solution have converged. So, our guess for 0.203 is correct. And we are to use the next larger commercial size equivalent to 22 centimeters. Okay? Not the 20. Okay? For conservative purposes. Always choose the next commercial size. So, we are about to be finished. Some explicit equations in order for us to solve for the Q and the discharge and the diameter. Ang daming sinolve, no? Pero, may madali pa ng paraan. Okay? So, however, there is a however line. If there are any losses, again, class B, that's why we need to know the hard part. Bago ka maglakad, matututo ka munang gumapang. Bago ka tumakbo, matututo ka munang maglakad. In English, you need to walk first before you run. Before you fly, you need to run. Right? Your airplanes, they need to have acceleration in the ground. So, here's our however statement before using this easy equations. Input, plug and play. However, if there are any losses other than friction losses, HF, you will still need to solve these equations iteratively. So, there is still this deadly word, iteratively. This tiring word, right? So, here's our problem again a while ago. We just simply input the head loss, the variables, right? The length, the discharge, the head loss, and the acceleration due to gravity. So one equation, one unknown, one formula. D is equivalent to 0.205. So that will be it. Alright. Before we had 0.203. So again, use a larger commercial size of 22 centimeters. Basic. So other empirical formulas that no need to memorize, no, because we are much concerned with Darcy-Weisbach, but then we can also use this. Hazen-Williams equation. So sorry about that. There is a motorcycle outside. So you can simply use this equation, right? So the coefficients or CHW is the Hazen-Williams coefficient with these values. Okay? So again, class, no need to memorize. Now for the Mannings, we have already used this. Actually, the Mannings will be very important for open channel. Okay? So we will use this when we talk about canals, when we talk about weirs. So we will much focus on Manning's formula. So look forward to it. So this is our equation for the Manning's equation. And Manning's constant. And for your Chezy formula, where C is the Chezy coefficient. And the Strickler formula. So these are very straightforward with very straightforward constants. So these are the relationships of each other. How you can relate the values of your constants for Chezy, Manning, and the Darcy and your Strickler formula. So just one equation, one example. New cast iron has a length of 6 kilometers, diameter of 30 centimeters or 0.03 meters with a discharge of 0.32 cubic meters per second at temperature 30 degrees Celsius. We are to calculate the head loss. Simply plug and play. A new cast iron will give you a constant of 130. That will be it. The diameter, simply input 30 centimeter. So convert into meters, 0.3. Right? And then, solving further, the discharge, 0.32. One equation, one unknown, HF, head loss, 333 meters, 333. For the Mannings, we simply have the Manning's constant to be equivalent to 0.011 for cast iron. This one given, 0.32. So independent of the length, dependent of the length, 6,000 meters. So solving further, one equation, one unknown, 470 meters. Okay. So I hope you learned something today, class. That will be it for our major losses. Thank you all, and God bless you all.